Right, okay, hello, this is the CFD Internal Flow Analysis tutorial. I'm Chris Bell, Powertrain Manager of TBR14. I'm going to show you how to use Ansys 14.0 Workbench to analyse your Internal Flow CFD. So the first thing we need to do is have our model ready in NX of what we want to CFD. So as you can see, this is the external shape of the first iteration of plenum for TBR14. So the way that we work with the Ansys CFD software is we need an internal volume to analyze. So this is the external volume. There's a very simple way of how to turn this into an internal volume, and the way we do that is this tool down here called delete face. If you haven't got this toolbar, if you just search for it in the command finder and search for delete face, you'll find it. So you click delete face, and then what you want to do from here is delete all the internal surfaces, so you're left with the external ones. So if you have boss or pocket faces selected up here on your face wall, and click one of the faces, hopefully all of the internal faces should have been selected, as you can see. Right, so what you can do now is if you use this tool up here, which is all but selected, click that, all the external faces should now be highlighted. So we should have delete face on all of the external faces. If we now click OK, we turn that external body into the internal volume that we're looking for, and this is the volume that we are trying to CFD. So we have the inlet and we have the two outlets. So what we do now is we say File, Export, and we want to export that as a step file. So when you export as a step file, you choose the location of where you want to export it. So that's as simple as that. You say you want to export the delayed part, the displayed part, data to export, select the object you want to export, which is that, just to make sure you've got the right one, and then just click OK. I've already exported this, so therefore I won't bother doing that, but you can then go and find your exported STL file. Once you've found your exported STL file, you need to move it over to the X drive. So this is now, I've taken you on to the remote desktop area. So on the remote desktop, I have now put on the X drive this step file that was created from that plenum. So what we do now is we go to Start in the X drive and we launch Ansys Workbench. So we go to Programs, Ansys, Workbench 14.0. You'll have to bear with me at points of this because it takes a very long time to load certain things. Right, okay, so Ansys is now opened up and this is the Workbench home screen. So the first thing we want to do is start a new CFX program or analysis tool. So double click on CFX and then wait a bit, and this little tool will appear here. So this breaks down the CFD into a number of different stages. First with the geometry, the mesh, setting up the conditions, the solution and the results. So the first thing we want to do is import our geometry that we've created in NX. So if you double click geometry, this will then take you to this screen. Just OK this little pop up here. So to import your geometry, all you do is go File, Import External Geometry File, find the step file that you've created, click Open, and then click Generate. And then there you have the generated step file. You don't need to save this. All you need to do now is just close that window, and this will then revert back to this home screen. So that geometry now has a tick next to it, and this little symbol here shows the mesh is awaiting an input. So if you now double click on the mesh, it opens the mesh screen. The geometry should be loading, so here we go, it's coming along. Right, so now we have a geometry in there, but the geometry isn't meshed. So as you see here, it says the mesh thing here. So the simple way to mesh it is generate mesh. Nice and simple. We now wait Right, so now it's finished meshing, so there's a tick next to the mesh, which goes show mesh, it shows the actual what it's done. Again, just close the box to go back to the other window. This one, if you right click, because it's got this lightning bolt next to it, and go update, what it should do is eventually come up with a tick. Right, so there we go, so the mesh has got a tick next to it, which now means we can go on to the setup. So again, double click the setup. If you just look down here at the bottom, it should say whether it's doing something, so it's saying it's starting the CFX pre. And that is this sort of setup tool. So once that's loaded up, it should take a bit of time. Once it's loaded up, it should have a window like this showing your imported geometry, and then this is the setup tool. First thing we're going to do is change the analysis type by double clicking it. So what I did there is double click this analysis, and we're going to change from steady state, we're going to go to transient. You don't need to worry about that. So what we have here is the setup of the transient. So we have this time duration option, and that is the total time of your simulation in the simulated state. So not a real world time of how long a simulation is going to take, but the overall time of a simulation. So for me, for the engine to do 2 cycles, it takes 0.014111765 seconds. And if there's 60 time steps, which is what I'm going to use, the time is for each time step is 0.0002353. So that's saying that a time step of 0.00 whatever in that many things. So there should be 60 time steps in that overall time. So that's that. So click OK on that. The next thing you need to do is double click default domain. That should all be fine. If you're using air for the inlet, you're using air at 25 degrees C, so that's fine. Fluid models, I'd go for no heat transfer, and then initialization, you want to click domain initialization, chord frame, and then just put 0, 0, 0 in here, and then the relative pressure is 1 bar. So you see, I just changed that bar by that and put 1 in there. So click OK. What's it saying? Oh, this is just a problem with this sometimes. Just do that, and it might. There you go. That'll work now. Right. So now we need to use the expressions for the transient pressures at the runners. So the way I did this was I took wave data from Ricardo Wave. I then took it into an Excel file, and what you need is a Excel file that looks like, hold on a second, I'm just going to go and get it for you. Right, so sorry, the last video finished quite abruptly because I didn't realise I had a time limit on how on each sort of clip that I produce. But I finished off trying to talk about importing the transient boundary condition data. Not very well, but I'll try and go over it again now. One thing you need to do with transient is state how your boundary condition is changing over time, and the way we do that is through an Excel file and then just turning that into just a normal text file. So essentially I created an Excel file with all of my pressures, so this is pressures in pascals, from data from Wave. So I created these 2 columns. As I said, there's 60 time steps, so there's 60 sets of data. Rather than having it against time, you just have it against the time step. And then if in Excel you just say you want to save your Excel file as a text file, it should produce something like this. And then this can then be read by the Ansys software, and then read as a changing pressure for the time step. So I've saved those 2 data sets on the X drive as well, in the same directory as the plenum step file. Right, so now the way we use those expressions is by, at the top here, there's a thing called a function and an expression. it's split into these two things, but what you need to understand is that all the function does is it's read by the expression. So the function reads the text files, the expression then just reads the function, and then your boundary condition is set by the expression. It's all very confusing, but hopefully this should become clear when I start to actually use it and show it. So I'll have two expressions, two transient positions, and that'll be at the end of each runner. So there'll be two functions, two expressions. So if you click this function button and then name one of your functions, so this will be the first runner, so I'll call it out1. The argument units is going to be the units of the time step, so that'll be seconds, and the result units is the units of the pressure, so pascals. What you then do is you right click in this white box here, you go import data, go away Max Cavell, and then you choose, this is very confusing here, but you choose the one which you want. So I want runner 1 data 8500 PM at 61 time steps. Click open on that. That should then appear like this. If it doesn't, then something's gone wrong. Simply then click these two boxes and then go OK, and you should now have this out1 user function under here. We want to do the same for the other runner, so we're going to go out2, same things apply, seconds, pascals, right click, import data. Do the other one, so runner 2, 61 time steps, OK, that's appeared again, extend min, extend max, OK. Right, so now we've got two user functions. We now want to have those in expressions, so we're going to call these the same thing, but they have to be slightly different, so I do it without a space, so it can determine different names, but they're the same thing. So I have this out1 expression. If I right click in this box and then I link it to the function, so I say functions, user, out1. What I now need to do is relate this to time, so between these two brackets I then type the letter T, that is a T, believe it or not, and then go apply. So now we have this out1 expression which has been created. If you right click and go insert another expression, call this one out2, do the same thing with the other data, out2, put the T in, apply. So now we have our two expressions, so you can click that now. So we've got two functions, two expressions which are linked to those functions. So now what we can do is we can add in the boundary conditions. So the boundary conditions that I want to add are one inlet and two outlets. So this is the boundary condition button, so click this. I want to add my inlet. There's only one of them, so boundary type is an inlet. For location, spin this so you can see the inlet. Click this little button here. And this is a really stupid way of doing it, but go through and try and find the surface of the inlet. So I don't think I've got it yet. There you go. So there's the inlet. So click OK on that. Boundary details. It's subsonic. We're going to have a total pressure stable of 1 bar. This is all normal. Just leave all these. Just click OK. So now you can see we have the boundary condition of 1 bar that's been applied. Now we want to apply the outlet conditions, so I'm going to call it runner 1. So you have to get it so you can see runner 1. Now choose in the same way by clicking that box. Actually, before I do that, we obviously need to change this to an outlet. Click that box and go through and try and find your runners. As I say, this is a really stupid way of doing it. Right, so I'll have runner 1 as the right hand runner. Okay. Now this is where it's different. Instead of average static pressure, change this to static pressure. So, and then we'll end up with this relative pressure. Now this is how we link it to the expressions that we created before. Click this box and call it the name of the expression. So you have to remember that. If you click OK, so that's fine. So we've now got that outlet that's been set. Do the same with the other one. So I called the first one runner 1, this is runner 2. It's an outlet. Its location is down here somewhere. Where is it? There it is. Boundary details, static pressure, this expression, out 2. Click OK. And you see we have the input and the two outlets, they've all been set now, and these have been set with the transient data. We have this message here saying that we're not actually quite finished, so this is, if this has a message in it, says that you need to sort something out, there's some error somewhere, and this is in the output control. So if you go into these things here, these solver things, and just make sure that these are all correct, so that one was right, solve control, that's really confusing, and output control. The one thing we have to do here is just go to transient results and create somewhere for the transient results to go. So just go OK on that. So create a new one, go OK, and then I use this output frequency of every time step. So it makes it really nice and simple. Go OK, that message disappears. Our setup is complete. So again, as we did before, just close it, and we should return to the normal setup box. So that now has a tick next to it, and we can go on to the solution. Double click solution. As you can see, the CFX solver manager is now going, so we know it's doing something. Right, so now the solver has appeared. All we need to do now is just click start run and then wait. I'm going to skip ahead to once the solver's finished, but essentially the graph should appear and it should do loads of stuff and then say that the solver solution's finished. I'll skip ahead to that now. Right, so the solver finally finished, and so this is what was produced. So just click OK on that. This is showing the solution converging over time, so this is for each of the time steps. I have no idea what any of this means though, but this is it finally finished. So this is the solver finishing, so you can just click X on that again. So now we should have ticked by everything other than the results, so we can double click on the results to analyse those. So I'll open up this CFD post analysis window, and what we have here is, this is actually the geometry of the plenum that we imported, but it's just a very basic version of it. So there is one way that you can display more of it. It's sort of a percentage of the mesh. If you double click this wireframe and change this amount of the degree, and by lowering the edge angle degree, you can see more of the plenum. So it's a toss up of how much you can see of the external and then how much you can see of the internal. I'll just quickly show you how to apply visible streamlines. It's extremely simple. You can literally just go insert streamlines, click OK, and then down here you want to say where you're going to be starting it from. Start it from the inlet, equally spaced. You can have as many as you want. 40 is quite a good number for this, and then the variable, we'll set it as velocity. Click OK, and then that's the velocity streamlines for this current time step. If you click up here on this little clock, you can go through each time step for the transient solution. So at the start there shouldn't be that much flow, so you see the streamlines are at low velocity shown on this little chart here, and then with increasing time the velocity should change through the different runners and change the flow direction and all that sort of thing. So you can add in your different colours and what's shown actually on the solution in buttons up here, so you can add sort of contour plots, you can add volume rendering to show all sorts of things, but just simply I'll show you how to add in the streamlines. Finally, to create a movie from this, what you need to do is create this little animation editor here. So move the solution into a view where you can see what you want, into the angle you want the movie to be made at. Click this animation, click time steps. This is the number of frames, so you want a lot of frames. Click loop, and then click save movie. Choose where you want to put it, so I'll have it as that. I'll save it just into this place here, save, and then by clicking play what it'll do is it'll just cycle through each time step and put together each of the frames for the actual animation. I'm not going to do that now because that's quite an annoying thing to go through, but I'll show you what it eventually produces. So it should produce something like this. This might be a different plenum. So once it's finished, it will give you something like this. So if there you go, not very good, but it will keep looping and keep producing that. So yeah, that is how to do transient CFD in Ansys using your NX CAD model. So I hope that was helpful. Yeah.